So now I have started recording. So first of all, you put in your attendances, and yeah, let me continue with the class. So yesterday we did Noether's theorem and understood what it means that when things are conserved, we can expect symmetry, and vice versa. Okay. So we tried to have an alternative point of view of physical laws that uh, perhaps instead of guessing the force and torques, we can start from symmetries and try to write down the Lagrangian for a system. Okay. And that would be useful in many cases as we will slowly progress towards that. Today we try to uh, kind of sketch the details of another conservation law, which is conservation of energy.
Sir,
Yes.
so just one doubt. So when we say that the Lagrangian is not unique for a system, right?
Yes.
So does it mean that like there can be in one coordinate system, like, let's say it's in Cartesian, we
Yeah.
can write the Lagrangian in like many forms, right? But
Yes.
does it mean that if the same thing we are dealing the same system in the other coordinate system, we can write the Lagrangian like in the terms of different coordinate system, and then the equation will be valid if we use even the generalized coordinates of the first system, initial coordinate.
All right. So if you have noticed that there is a new homework in the uh,
Yes, sir. I actually solved it, but that is exactly the confusion. I came to the result, but there was this loop hole in my concept actually.
the point is that if Lagrange's equation is satisfied in one coordinate system, it will be satisfied in any coordinate system that is uh, related to the old coordinate system by a point transformation. So you want me to give away the answer right now, or perhaps you want to wait before the others have their fair share of trying, and then I can come back to this.
No, sir,
Uh,
I don't want you to answer that. I actually just mean to like clarify something. Like we are using different generalized coordinates, right? Q, small q, and capital Q in that question.
yes.
And I just want to ask, like, if we are using Q or Q, like small q and capital Q, it will not matter like which Lagrangian we are using, right?
No, the here these two Lagrangians are not two different Lagrangians, by the way. So this is the
Yes, yes.
same Lagrangian written in different coordinates.
Okay, okay, sir. That's so. Actually, I spent like whole night wondering about this.
No, no, it's
That's
not a different Lagrangian. It's the same Lagrangian expressed in a different coordinate system.
okay,
Okay,
okay, sir.
so
Thank you, sir.
those two things are different. Okay, all right. Uh, okay. Uh, so, since you raised this point, I have a minor comment about homework one. So, in homework one, the second problem was that you were given a Lagrangian, which is half m x dot square minus v of x plus x dot, I guess. And you were asked to find out the equation of motion. Most of you did, and you recognize that this is your Newton's second law. And then I asked you to interpret the results. Apart from one or two people, most I think most of you missed the point. So you were satisfied that you got the Newton's second law, and that's probably the interpretation. But if you think about Newton's second law, the Lagrangian then stops here, right? It's just kinetic energy minus potential energy. Okay. So there is this extra piece. So when you try to get Newton's second law from Lagrangian formalism, you write the Lagrangian as just half mx dot square minus px. You don't write this part. So I wanted you to understand what this part was doing there. So the answer would be short that this part can be written as the total derivative of half x square. Okay. So since this is a total derivative of something that depends on coordinate, so this part does not affect the equation of motion. So the effective Lagrangian basically stops here, and that's why quite legitimately you get Newton's second law. So this was the final interpretation. A few people did write this answer, but many people did not. So I kind of wonder, did you miss this point, or it's a problem of your writing skills that you could not express it? Okay, or if I was not clear enough during my lectures. If it was not clear, you can tell me, but this is a small point. I expected you that you would catch this actually, and I am surprised that many of you did not get uh, this small point. So if anyone can you tell me if it was not obvious to you, or did you face any problem in getting this point?
So actually, probably most of, including me, we thought that the point was like we can obtain the force equation without using, like we can calculate the force without you knowing the initial acceleration or whatever the acceleration equation was. So I think we interpreted it in that way.
I see. But when you saw that this is Newton's second law, you should be surprised that this doesn't seem like the Lagrangian, the usual Lagrangian for Newton's second law.
Yes,
Uh,
yes, that point actually was clear, but like in the homework, it was written like, what do we interpret from this result? So we thought that we must relate it with the coordinate and their derivatives, first or second derivative, like generalized coordinates. We
all right,
interpreted.
it's okay. Perhaps the language, the phrasing of my homework was a bit ambiguous. It might be possible. Anyway, so hopefully now you get this point.
But actually, I actually thought that
Yeah.
the Lagrangian, you said the Lagrangian is not unique and Lagrangian is not always the form of t minus v. It can be of any form, any other form. So I thought that this is one of that other form. I that that in the
Yes, but the point is that see, L equals t minus v is also a valid Lagrangian, and this seems to be a valid Lagrangian as well. Okay.
but this is not the only way.
Yes, but so if someone writes L equals t minus v, the point is for Newton's law you can write L equals t minus v. If there are systems for which you cannot write L equals t minus v, then your point of view is valid that Lagrangian is not meant to be t minus v. But for Newton's second law, we know that L equals t minus v works. Now I come across another Lagrangian which also works. Okay, so now I mean to wonder whether these two are related somehow. Okay. So I will give you an example of a system where L is not t minus b, and you cannot write it L as t minus b. So this possibility is not there. Okay. So if this possibility is not there at all, then you are valid in thinking that okay, this is what it is, and there is no like, further uh, mm, further simplifications I can do to it. But here you can do one level of simplification. It's all right. It's all right. I just yeah, just to just tell you that be watchful in future, and yeah, try to explore every corner. Okay. So and that's why I allow sufficient time for homework so that you can think before you get to your final answer. You just think and then write down your well thought out answer. It's not that I gave you an homework and I am trying to see how quick you are. Okay. So I personally believe that it's important to be correct than quick. Okay. So yeah, that's so think about every corner. Take your time. No hurry in there. and express your approaches clearly. And I have noticed that some people are not writing the details of your mathematical steps, and there will be uh, actually penalties if you do not explain your steps. And there are, I think, one or two people who in their handwriting do not distinguish between partial derivative and total derivative. So you have to distinguish between this d and this del. This should be clear from your handwriting. Okay. If it is not clear from your handwriting, I will not accept an excuse that this is because of the handwriting you could not distinguish between that. So make up a way where you use this d and this del. Okay. And by the way, uh, do not use this delta for a derivative. So if you do things like this, say delta L, delta Q, something like that, this doesn't mean partial derivative actually, and this delta has a different meaning. It's called the functional derivative. So do not use this delta for derivatives. Okay. So if these things are unclear to anyone, I would recommend that person to check out the basic multivariate calculus first. Okay, what do I mean by total derivative and partial derivative? You have to distinguish between that, and that is a very important mathematical background that you must have so that you can follow this course smoothly. If you do not know the distinction between this and this, then you will perhaps be in dark on what I am about to say here or what I will be doing here. Okay, so make sure you do that. Okay. And all right, so now let me come to the main point of today's class. So I will start with the derivative of the Lagrangian. So my Lagrangian actually is a function of the coordinate and the coordinate derivatives. Okay. Let's say like this. All right. And so if I take the total derivative of the Lagrangian, so why I am taking the total derivative of the Lagrangian, it will become clear in a moment, so that I have something in mind. Okay, so for now I am just curious what happens if I take the total derivative of the Lagrangian. So this is sum over k del L del qk dot plus again another sum over k del L del qk dot and then qk double dot and del L del t. Okay. So now what I can use is the Lagrange equation itself. So I noticed that this piece here, I can replace this, that this should be equals to d dt of del L del qk dot, or what I mean, this is dpk dt, because del L del qk was my generalized momentum, which I denoted as pk. Okay, so this should be dpk dt, which I will denote as pk dot. Okay, so what I have here with these things, what I have here is summation over k. So this term is just pk dot qk dot plus, so this guy is again pk. Okay, so pk qk double dot plus del L del T. Okay. Now the term under the summation is quite interesting. So this, if you notice carefully, you can write it as d dt of summation over k pk qk dot. Okay. So from the product rule, you can check just this is this plus del L del T. Now, if you rearrange, so here you have d dt of something, and here you again have d dt of something. So you just put all the ddt's together and write this thing as like this. So standard way of writing this would be, so d dt of summation over k pk qk dot minus L, so, and that should be equals minus del L del T. Okay. So this quantity inside the bracket I will denote by H, okay, and I will later call it the Hamiltonian of a system. So, and it is defined by that, and this then gives you dH dt equals minus del L del T. Okay. So what I notice here is that if L does not depend on time explicitly, so suppose L doesn't depend on time explicitly, that means del L del T equals 0. So this will imply dH dt equals 0. So H will be conserved. So H is a quantity, this whatever this Hamiltonian is. So H will be conserved when del L del T equals 0. So these conserved quantities are very important because these conserved quantities, since it is a constant of motion, basically conserved means that it does not change with time. So if you can know the value of the Hamiltonian at one point of time at any time, then it will stay there for ever. Okay, so it will never change in there. So that becomes a constant of motion, and you can use that constant to uh, to express many simplify. You can use that constant to express many quantities, physical quantities. For example, if you remember, in the case of central force problem, the L, the angular momentum, was a constant of motion, so it does not change with time. So when you try to find out uh, uh, the equation of an orbit for under the central force problem, and it becomes a conic section, it becomes usually an ellipse if the eccentricity is less than 1, and that eccentricity was related to the angular momentum also. Okay, I guess so. Since L by R equals 1 plus cos theta, not the eccentricity. I think the length of the major and minor axis, perhaps. But anyway, you can see that you can find out kinematic quantities in terms of those constants, and it makes your life easier. But for now, this Hamiltonian is an abstract concept. It's just abstractly related to this Lagrangian, this PQ dot minus L. But what is this Hamiltonian actually? Okay. So can I figure out any spatial significance of this Hamiltonian? So does H have any spatial significance? In some spatial cases at least. Significance. So what we intend to prove is that in the cases where the Cartesian coordinate are time independent, this H can be related to total energy. So H can sometimes be related to the total energy of the system. How do I see that? So suppose that your Cartesian coordinate, if you have n number of particles, suppose there are n number of particles, and the alphath particle the coordinate for alpha particle in 3-dimensional thing. So alpha, suppose, is 1 up to capital N. So there are n number of particles. And there are constraints also. Suppose there are 3 particles like connected via rigid rods, okay, massless rods here. So they will have, so this one would be R1, this would be R2, and this will be R3, but there will be 3 constraints also. So the length of this is constant, length of this is constant, and length of this is constant. So, so this R's by itself will not be very useful because there are constraints. So better you move to some generalized coordinates. You just make the m number of independent coordinates. Okay. So from this n number of coordinates, you go to say m number of independent coordinates, and you call them say q1 up to say qm. Okay. So what you do is that, so let me call it capital M because I'm calling it capital N. So what you have is that you have change your R alpha as a function of this q1 up to qm. Okay. And what I require is that these equations are time independent. Okay. That means these constraints are time independent. So this length is not changing with time. What I mean by that essentially in to put these things into context. So the constraint equation are time independent. That means these relations would be time independent. So, okay. I mean, uh, so what I mean is explicit time independence. Of course, these the individual coordinates would depend on time. So in such cases, I intend to prove that H would be given by T plus V, the kinetic energy plus potential energy. Okay. So if these constraints, equation of constraints, do not depend on time explicitly. So how do I proceed to prove that? So first of all, let us find out how T and V look in terms of the generalized coordinate. Okay. So so first you need to find out so how do T and V look in terms of the generalized coordinate. Okay. So for V is trivial. So V is usually a function of R. So you change it to, you replace R by Q1 to Qm by this equation, and then then V becomes a function of Q itself. So that is trivial. You just replace the coordinates that are involved in V by Q. Okay. So V is usually a function of coordinates only. So you replace this V with Q. Now, what about T? Okay. So T would be given by, the kinetic energy would be given by half summation over alpha. So m alpha r alpha dot square. Okay. I mean the magnitude square. Okay. So you sum over the kinetic energies of all these particles that are sitting here, here, and here, and you get your kinetic energy and the total kinetic energy of the system. It looks very reasonable. Now I have to change this R alpha dot here. This R alpha dot using Q1, Q2 up to Qm. So for that, I need to use this equation. So this, from this equation, I can easily obtain that my R alpha dot is basically equals summation over K. So del R alpha del UK QK dot. So that's what I mean. And of course, this K would be 1 to M because this runs over these indices. How many Q's are there? Okay, so and this equation holds for every alpha. Okay. Good. Now Now you can find out R alpha dot square. So this R alpha dot square, that would be just R alpha dot dot R alpha dot, and this is nothing but just taking the dot product of two of these things. Okay, so I will write it as, and notice this. So I will write 2 R alpha dot here. So the first R alpha I write as summation over k del R alpha del qk dot. Okay, and then the second R alpha dot I write as I have to change the index here. This is very important. Okay, and you cannot use k here because the k sum, the index of k is already used up here. So the details of this you should probably understand in your tensor analysis course. Have these things have been discussed in your tensor algebra or tensor calculus courses, that you have to use different indices in such cases? Okay. So here k runs from 1 to m, j also runs from 1 to m. Okay, so you can now put these things together and to write, say, summation over k and j, and then I will have, sorry, del R alpha del qk times, or here there's a dot missing, dot del R alpha del qj. Good. And times qj dot qk dot. Okay. So using this in here, I can write, so this t will be equals to, let me use a different color. So this t will be equals to half summation over alpha I will write later, but first let me write summation over j and k, then summation over alpha m alpha, then del R alpha del qj dot del R alpha del qk times qj dot qk dot. Okay, which using a shorthand I want to write as half summation over jk, this quantity inside, what color do I use? Maybe red is. So this thing I call mjk. Okay, so this mjk times qj dot qk dot. Okay, this is, as expected, is a quadratic function of generalized velocities, and where I have defined my mjk as summation over alpha m alpha del R alpha del qj dot del R alpha del qk. Okay, so if you notice, if you interchange j and k, this does not change. So this means this is a symmetric matrix. So symmetric matrix. Okay, it runs from the indices j and k. Good. So this is my t. This is the value of t. So that my t becomes this. This is my kinetic energy. Good. All right. So if this is my t, then if I try to figure out what is my pk, so pk will be given by del L del qk dot. Now notice this derivative only picks out the q dot dependent term from L. So the q dot dependent term, the velocity dependent term in the Lagrangian usually resides in the kinetic energy part. The potential does not depend on velocities. Okay, so you see that the potential does not depend on q dot. So it is independent of q dot. It is usually function of coordinates for systems that are conservative. I am implicitly assuming that, of course, here. Okay, for systems that are conservative, the potential usually depends on the coordinate only. So this del L del qk dot essentially is del T del qk dot. Okay. Because for systems that for which you can write L equals T minus V, and this del L del qk dot is just del T del qk dot. Now, what is del T del qk dot? You have to find out from here. Okay, so this is the expression of T. You have to find del T del qk dot. Rather, so so that I can do it properly using tensor algebra, I would calculate, say, I will change the name of these generalized coordinates. You'll see in a moment what I mean. So del T del qk dot would be given by del qk dot, okay, and of T, and T is what? T is half summation over J and L. I changed the name of the dummy index because it is summed over, so it doesn't matter whether you use K or L. It's MJL QJ dot QL dot. Okay, so you have to take this derivative, and if you take the product rule of the derivative, if you check the product rule of the derivative, then so the half comes out first. So the first term would be summation over J L. So M J L. So that will be del QJ dot del QK dot. Okay, and that is just delta JL. Delta JK. Okay, plus similarly summation over JL. Add another page here. Then MJL and MLK.
Here will be a QL, I think.
Yes, I missed QL dot, right? Thanks.
Yes.
So let me, what this will be? This will be KL, and here I missed QL dot, and here I guess I missed QK dot. Great. So now if I write down, so PK would be given by so half. So I take the Kronecker delta and just impose J equals K. So this is summation over L. So J equals K means M KL QL dot plus summation over, here it will be summation over J. So it will be M JK. This impose K equals L.
Sorry, it will
No,
be
no, 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 no.
QL QJ dot.
QJ dot, yes, sir.
Yeah. Perhaps, yeah, it will be QJ dot. So this is QJ dot. Notice that since MJK is symmetric, so this is symmetric, so you can write this as MKJ. And since J is a dummy index here and L is a dummy index here, these two terms are the same. So it's basically 2 times that, and so you write this as, so summation over J MKJ QJ dot. So that is your PK. Okay. Now, so if I now try to figure out what my Hamiltonian is, so Hamiltonian should be given by summation over PK QK dot summation over J, summation over K minus L. And notice what happens here. So I take summation over K out, and this PK is summation over J MKJ QJ dot. and then there is qk dot minus L. L is just T minus V, so I am just going to put it there for conservative system. I am implicitly assuming conservative system here. It's only true for conservative system. So this is summation over Jk M Kj Qj dot Qk dot minus T minus V. All right. So if you again go back to the expression of the kinetic energy was this half mjk qj dot qk dot, and so this fellow here, this thing here is just 2 times kinetic energy, because half of that was my kinetic energy, and 2t minus t minus v should be just t plus v. So we learned a lesson that if we are dealing with a conservative system and we are dealing with constraints that do not explicitly depend on time, then this Hamiltonian that I found out. So Hamiltonian, remember, Hamiltonian is more general than total energy. Okay, so it's only in some special cases it reduces to total energy, and that special case is when you are dealing with conservative system and dealing with constraints that do not explicitly depend on time. Okay, so in those cases, Hamiltonian is just T plus V. So more abstract users of Hamiltonian, I will come to that. But for now, notice that if the lesson you learned from this lecture is that if L does not depend explicitly on time, then a quantity which I call the Hamiltonian is conserved. I do not understand at this point what this Hamiltonian is, but for a conservative system and for time independent constraints, I can interpret it as my total energy. Okay. So I pause for a brief moment here to take questions if there is something unclear in between.
So last third point, I did not understand.
The third point, sorry.
So this one, just after pk in that step, where summation over j m kj qj dot and the yes sir.
This part you did not understand.
Yes sir.
From here to here, you did not understand.
Yeah, yes sir.
Actually, you see, this one and this one, they are the same thing. First, try to realize that. Okay, because here there is summation over L, right? So if you break it up, L
Yes sir. Got it sir. Thank you sir.
Okay. Anything else? All right. So I hope there are no further questions. So the next topic I intend to cover, I don't know if I will have time in today's class, but let me try to introduce that. So this I will call say velocity dependent potentials. Now, so far we have been dealing with conservative system. So conservative system is a misnomer. I would not use that word. I would say that we were dealing with systems for which a potential formalism can be found for the force law. Okay. So you could find out a scalar function, and if you take a space derivative of that scalar function, you get the force. And if you try to figure out why that was possible, for some cases when, so remember here I said that the potential is a function of r only, okay, the coordinates only. So it was possible because if you try to go back to the region, the usual force laws that you are used to are always depended on coordinates. For example, take the example of harmonic oscillator. So this F equals minus kx. Okay, so the force only depends on coordinates. Gravitation, F equals g m by r square. Same for Coulomb's law, electrostatics. Uh, what else I can give example of? Okay, so you see that these force usually depends on coordinates only. Okay. But even if the force is like more complicated, it usually depends on coordinates, and then you can kind of guess that if there is a scalar function that depends on my coordinates, uh, then I can take the space derivative of that scalar function and I get my force law. But what happens if the force law itself depends on velocity? So I am trying to backtrack a bit. So I am trying to give you known examples. So usually my ultimate goal is not to use the language of force at all. So for that, I need to give you an impression. I need to give you an example for which this formalism that force is kind of you can get from a potential breaks down. Okay, so in these cases, you find a scalar potential. But there is another force actually that you have learned in your earlier courses. That's the Lorentz force law. Okay, so this force, if there is a charge moving in a electromagnetic field or a magnetic field rather, so the QE plus V cross V. Okay. So as long as it was pure electrostatics, there was no magnetic field associated with that, then your force would be still dependent on XYZ actually. But here you see for an example that your force law depends on velocities. Okay, not only just the coordinates but the derivatives of the coordinates. And that's why you usually never hear about a scalar potential corresponding to a Lorentz force. Have you ever heard about that? Nobody talks about a scalar potential for a Lorentz force, because Lorentz force is a different kind of beast uh, that needs some special care to treat. Okay, so that's why. So here you come across the first example where your potential description of force breaks down. So you have to find out an alternative way of dealing with things. Okay, and that's why when you do problems using Lorentz force law, you directly start with the force. Okay, you never go back to the potential and so on. That complicates things. So and so I want to stress this point. So this is the disadvantage of working with force. So for different types of forces, you need to take up different strategies to tackle practical problems involving that force. Now the Lagrangian formalism, if it takes away the force element of from the problem, then that gives you an unified platform. Okay, for which you can describe any system. So the Lagrange's formulation doesn't depend on whether your force is conservative, on whether it can be described by a potential or not, and so on and so forth. And that's why Lagrangian formulation. So when we have to treat an unknown system, we usually trust on the on the Lagrangian formulation, and we always approach any unknown physics problem from the approach of a Lagrangian. We try to figure out the Lagrangian. Okay, so for example, if I want to treat this in my Lagrangian formulation, so how do I do that? So uh, how to write down the Lagrangian for such, let's say, forces. Okay. Right, and now you see that since there is no V, L equals T minus V doesn't work. Okay, you cannot write things as L equals T minus V. So you are stuck, right? And actually there is to be able to write down the Lagrangian corresponding to this, you have to trust on symmetries, but that will come later. Here I will do that. I will take kind of a bottom-up approach to try to figure out from a bottom-up approach what the Lagrangian should look like to get an idea. Okay, and for that, so I will do that in the next class. By the way, the detailed thing I will do it in the next class. For that, I need you to like test your background of electrodynamics. So I want you to understand the basics from where B equals del cross A, Maxwell's equation, and E equals minus grad phi minus del A del T. These things come from, where do these things come from? And what do I understand by the gauge freedom, or the gauge choices? Okay, so different thing called low range gauge and Coulomb gauge. Okay. So I mean, what I mean is that this phi and A are not unique. Okay, so they are related by the gauge transformation. What you understand by that, and perhaps from there, from if you learn this part quite well, then you would be able to follow what I'm going to do the next class. But for now, you can tell me. So this course, this lecture officially ends here. So now you can tell me, does every one of you know this well? Okay, so you know about gauge freedom, you know what is Coulomb gauge, what is low range gauge. Okay, what do I understand by gauge freedom? So has it been covered in?
Yes, sir.
Okay, very good. So yes. So that will be my next class. Anyways, so now I will end the class here. So if you have questions, you can ask me now. I do not want to start something new and stop midway. Yes.
When we write generalized velocity,
Yes.
then why don't we write it like del by del t or del r by del qj? We only write it like r dot, like only one time there is differentiation. In that they have been written.
Here you mean?
Yes. So when we write r alpha, then we write it down like del r by del qj into del qj and summation.
Yes.
But when we write the derivative, then we only differentiate with respect to qk. We don't write it like del by del t, d by dt of del r by del qj. It should be two terms. But we
Yes,
write it
that is a proper velocity. And qk dot, so this part is my generalized velocity. So in general, by velocity I mean derivative of the coordinates. So if qk is my coordinate, the derivative of qk is my velocity. So if I call qk to be my generalized coordinate, I call qk dot to be my generalized velocity.
like when we are taking derivative, then why don't we write d by dt of del r by del qk? When there are two terms, then one by one we take. Na? Why are we ignoring the term d by dt of del r by del qk qk?
This time, why I am ignoring this?
No, d by dt, like when we write r alpha, we write it down like
R has no explicit time dependence. It will be 0, I think.
You are asking about this, so this is from this it comes.
So when we write it like r alpha is equals to like dr alpha is equals to del r alpha divided by del r alpha divided by del qk qk summation.
Qk dot, yes, that's what I have
Yes.
written.
No sir, qk, and then when we take time derivative, then there should be two terms. I mean,
I don't understand why there should be two terms. I do not understand. This is the chain rule of derivatives, right? So tell me, this is, I am not sure if I am getting this point. So suppose f is a function of a multiple variable, is a function of say x, y, and t, let's say, and you want to find df dt. Okay, so how would you do it? Tell me.
So I'm talking in another sense.
How do we want to talk about it? You want
Like
to
R is like take it like R is a function of Q1, Q2, Q3, right? Like this. Then dr is equals to del R by del Q K into my Q K summation over K. Like simply I'm writing
so
differential.
so you are talking about this.
Yes. Like write in form summation.
Yeah, summation is there. Let's say let us simplify thing here. dy plus del f by del t
Yeah.
dt, right?
Then it generalized to del F by like del R into del R at summation over K.
Yes, now you
So
divide by dt, right?
right.
You come here. So here comes dt, here comes dt. That's what I have written.
Okay.
It is not clear to you?
I'm not sure. I need to see it again.
Yeah,
I didn't-
just check it. Yeah, check it. Yeah, take your time and check that explicitly. If you do not like the summation, perhaps you are being confused because of the summation. Do not use it. So suppose this is just a function of two coordinates. There is just q1 and q2 and nothing else. Write it in your own way. Okay. And then if you still have confusion, you can ask me on Monday. No problem. And you can also ask your friends for help. I guess these are things that your friends can help you with. Okay, and I really want a mixture, like real interaction between you guys. So please do interact with each other.
Sir,
Yes.
so just one request. Like, can you take like half a lecture for specifically for like constraints and like type of constraints, all those
Oh,
things?
the holonomic constraint and scaleronomic constraints, things like that.
Yes, sir. So I have never like previously studied
Yes,
those.
sir. Yes, sir. There is some more doubt on those topics. Please take one or two half class, sir.
Half class will be enough, sir. I think.
All right, all right. I would give you some examples and how to deal with constraints. Okay, I will do that. I'll
So
keep
because
that in
like
mind.
here we also talked about like Q1 to Qm, which are like independent coordinates, right? Independent.
Yes, yes.
So like they come in play when we are dealing with like constraints and all those things. That's why we actually want that.
Okay, okay. Perhaps in the next class I will have a short discussion on how to deal with constraints. No problem. Okay. Anything else you want me to discuss?
Sir,
Sir.
Yes.
Hello, sir.
Yes.
Sir, just yeah, sir, last example you discussed where f is function of x, y, and t, just so that, and if you will do functional derivative there, then that will be same as df and delta f. I
Yes,
mean,
but that so functional derivative does not apply there. Functional derivative is the derivative of a functional. So functional. So in the first class I talked about functional and function of a function, right? So things that are
yes.
functional, like the action, for which you can define a functional derivative. In fact, this thing that you were writing, I might be missing a factor of uh, del L. Sorry, let me use one coordinate, ddt of del L del Q dot minus del L del Q equals 0, right? So, and remember this Q is a function of t, right? It's a path, okay? And so this derivative in short can be written as del L del Qt. So this is the functional derivative of L with respect to this one, and you can just write it that. So I intentionally avoided using the functional derivative things because it should be substantially new, and it is always better to open it up like that. But this thing as a whole serves as a functional derivative. So this usually is written. Perhaps a bit more detail would be given when I try to cover classical field theory. Their functional derivative is there. So functional derivative are applicable when you are dealing with a functional. For example, this thing comes from an action. So action was a functional. Okay. So you input a function, you get a number, and then you can define a functional derivative. Okay. I do not know if that answers your question or not. So your is that what?
Yeah, yes, sir. I got it.
Yeah. Yeah.
Sir,
Yes.
sir, I have a doubt that in deriving the Hamiltonian,
I did not derive the Hamiltonian.
sir,
But
sir,
anyway, we carry on. I didn't derive the Hamiltonian. I got a quantity which I called Hamiltonian.
the t plus v quantity, and
Yes.
will you move it the side there?
Okay.
Yes, sir, sir. So
Yeah.
here where you have written 2t, it's because
2t. Yes.
yes, sir. So it's because it's a second order homogeneous equation, so forming a qj dot and qk dot.
No. It's not because of that. Not that complicated. That's because t is half times that quantity. So
Yes,
t
sir.
is just half of mjk qj dot qk dot. So if you are only interested in this blue part, so you put this 2 here. That's it.
So
What you are, yeah.
my question is if it's not a second order and it's like three terms are there for suppose qi dot qj dot and qk dot.
Then it will not work. Definitely, it will not work. I mean, I will not call that thing a kinetic energy. Kinetic energy is usually reserved for things that are quadratic in there, but then it does not work. Yeah. So here, I'm implicitly assuming that t can be expressed as half mv square. That means I'm implicitly assuming that I am doing non-relativistic mechanics.
I was just thinking that it's some form of generalized that we can take for any homogeneous equation.
No, not necessarily. Okay.
Yes, sir.
Sir,
Anything else? Yes.
yes. Sir, there is a student whose name is Paljor Lepcha. He didn't get your invitation, sir. So he didn't join.
Really? I mean, so is he officially registered? Because I think
I, I I don't know, sir, but he's attending two class. One is quantum mechanics and another class. So I don't know, sir. If,
he's from physics.
yes, sir. His physics and his roll number is
Let me
just a
check.
second.
Because you know the astro students do not attend this class. So if
Yes, sir. His roll number is 19, sir. I don't know he's registered or yet, but he's attending quantum mechanics class, and he said.
let me check the student list. So 19. Oh, okay. I now see Palzor Lepcha.
Yes,
Huh.
sir.
Oh, strange. Okay, I will add him. Okay. Yeah,
Okay, sir.
this is strange. Okay. Okay, so I will add him. Okay. Anything else?
No, sir.
All right then. So I end today's session here, and I will see you on Monday. So.